And to appreciate the technical audacity of the Raptor 3, one must understand that full-flow staged combustion was, for decades, considered a paper engine concept, a theoretical ideal that lived in textbooks but died on the test stand. While the gas-to-gas advantage provides a masterclass in combustion efficiency, the price of admission is an engineering Faustian bargain. To achieve full flow, a designer must solve the problem of the oxygen-rich preburner. And in the world of high-performance rocketry, heat is the enemy, but chemistry is the executioner. To drive a turbopump, you must generate high-pressure gas by burning a small portion of your propellants in a preburner. However, you cannot burn them at an ideal ratio, or the temperature would instantly vaporize the turbine blades. You must intentionally detune the reaction, running it either extremely fuel-rich or extremely oxygen-rich to keep the temperatures within the metallurgical limits of the hardware. And for 60 years, the global aerospace industry chose the fuel-rich path. It was the safe bet. In a fuel-rich environment, you have hot gas composed mostly of unburnt fuel. While this is thermally taxing, it is chemically manageable. But the Raptor 3 does not have the luxury of choice. Because it is a full-flow engine, it must process all the oxygen through one turbine and all the methane through the other. This mandates the existence of an oxygen-rich preburner, a device that creates a high-pressure, high-temperature stream of gaseous oxygen that is, for all intents and purposes, a universal solvent for metal. And the universal solvent, chemistry as a weapon. In our daily lives, we think of oxygen as the breath of life. In the context of a 300-bar rocket engine, oxygen is a terrifyingly aggressive oxidant. When oxygen is pressurized to hundreds of atmospheres and heated to several hundred degrees Celsius, the standard rules of materials science are suspended. And under these conditions, the chemical potential of the gas is so high that the distinction between fuel and structural hardware disappears. In a standard fuel-rich engine, if a turbine blade rubs against its housing, it might cause a mechanical failure or a flameout. In an oxygen-rich environment, that same friction creates a tiny spark. In the presence of hot, high-pressure oxygen, that spark doesn't just fade. It initiates a self-sustaining combustion of the metal itself. The turbine, made of high-strength superalloys, becomes the fuel. The engine literally eats itself from the inside out in a process known as oxidizer-rich transition. And for the materials engineer, this is the equivalent of trying to build a high-pressure boiler out of solid sugar and then filling it with boiling water. The very substance you are trying to contain is actively trying to incorporate your container into its chemical reaction. This is why the oxygen-rich preburner is often referred to as a contained explosion that is 1 microsecond away from becoming an uncontained disaster. And the historical ghost, from the NK-33 to the RD-180. The pursuit of this technology is not new, but its successful implementation is incredibly rare. The Soviet Union was the first to tread into this valley of death during the moon race of the 1960s. While the United States focused on the fuel-rich cycle for the F-1 and the RS-25, Soviet engineers like Nikolai Kuznetsov realized that the high density of liquid oxygen made it an excellent working fluid for turbines. And the result was the NK-33, an engine that utilized oxidizer-rich staged combustion. It was a marvel of its era, but it was not full flow. It only ran the oxygen through the preburner, while the fuel remained liquid until the main chamber. Even this partial step required the development of specialized stainless steels and coatings that were kept as state secrets for decades. When the Soviet N-1 moon rocket program was canceled, the engines were ordered to be destroyed. Instead, they were hidden in a warehouse, appearing years later to shock Western engineers who believed such a cycle was practically impossible to stabilize. And the Raptor 3, however, takes the challenge of the NK-33 and the later RD-180 and doubles it. By moving to a full-flow architecture, SpaceX isn't just managing one difficult turbopump. They are managing a symmetrical system where the oxygen-rich side must perfectly balance the fuel-rich side. They have taken the most dangerous secret of Soviet rocketry and integrated it into a high-cadence, reusable architecture. In hardware-level memory safety, the SX500 breakthrough. For a computer science professional, the challenge of the oxygen-rich preburner can be framed as a memory safety problem at the hardware level. In a language like C++, a buffer overflow allows data to spill out of its assigned memory segment and overwrite the instruction pointer, leading to a system crash. In the Raptor 3, the hot oxygen is the data, and the turbine manifold is the memory segment. And if the oxygen leaks its thermal or chemical energy into the metal of the turbine, it is a segmentation fault of the most literal kind. The process, which is the combustion, escapes its sandbox, which is the flow path, and begins to execute its logic on the operating system, which is the engine structure. To prevent this, you cannot rely on software patches. You need a hardware-level architecture that is memory safe by design. And this is where the exotic metallurgy mentioned in Chapter 3.2 becomes the protagonist. To survive the superacid environment of the oxygen-rich pre-burner, SpaceX could not rely on off-the-shelf Inconel or standard aerospace superalloys. These materials, while impressive, possess a burn pressure lower than the operating pressure of the Raptor. If a single grain of sand or a microscopic metal flake were to strike a turbine blade made of standard materials at 300 bar in a hot oxygen stream, the resulting spark would ignite the blade. And SpaceX's solution was the development of SX500. This is a proprietary, monocrystalline superalloy designed specifically to be inert in high-pressure oxygen environments. By manipulating the molecular lattice of the metal, SpaceX created a material that effectively lacks the hooks for oxygen to grab onto. It is a hardware-level sandbox. SX500 ensures that even if there is friction, even if there is a strike, the fire cannot find a foothold in the metal. It is the aerospace equivalent of writing a kernel in a memory-safe language like Rust. It eliminates an entire class of failure modes that have plagued liquid rocket engines for half a century. And the turbine hurricane, aerodynamics in a lethal medium. Beyond the chemistry, there is the sheer mechanical violence of the turbine environment. The oxygen-rich turbine in the Raptor 3 must extract tens of thousands of horsepower from a gas that is as dense as water, but moving at supersonic speeds. And imagine a hurricane, but instead of air, the wind is composed of pure, searing oxygen pressurized to the level of the bottom of the ocean. Now, place a series of spinning blades in that hurricane, rotating at over 30,000 RPM. The centrifugal forces on these blades are so immense that they are constantly on the verge of flying apart. At these speeds, the tip speed of the turbine blades can approach the speed of sound within the medium. And in a traditional engine, you might use a shrouded turbine to manage the flow, but a shroud adds mass and creates more surface area for the oxygen to attack. The Raptor 3 design must balance the aerodynamic efficiency of the blades with the chemical surface area exposed to the oxidant. Every curve, every fillet, and every cooling hole in the turbine must be optimized not just for the flow of gas, but for the prevention of stagnation points areas where the hot oxygen might linger long enough to find a microscopic imperfection in the metal's protective oxide layer. And the nightmare of sealing, perhaps the most understated engineering nightmare of the oxygen-rich cycle, is the interstage seal. In the turbopump, the turbine, driven by hot gas, and the pump moving cryogenic liquid oxygen sit on the same shaft. They are separated by only a few inches. And on one side, you have liquid oxygen at negative 180 degrees Celsius. On the other, you have gaseous oxygen at 500 degrees Celsius. If these two meet across the shaft, the temperature gradient alone can cause the shaft to warp, leading to a catastrophic rub. But there is a deeper danger, the bearing lubricant problem. Traditional bearings use hydrocarbons or oils for lubrication. In an oxygen-rich environment, oil is an explosive. And the Raptor 3 must use process fluid bearings, where the liquid oxygen itself acts as the lubricant. This requires tolerances so tight they are measured in microns. The seal must be absolute. If the gaseous oxygen from the turbine leaks into the pump side, it can cause cavitation and pump failure. If it leaks to the outside world, it creates a blowtorch that can sever the engine's plumbing. SpaceX's mastery of these seals is what allows the Raptor 3 to be a closed system, where no gases are wasted and no fires are unintended. And the pinnacle of a 60-year quest. When we look at the Raptor 3, we are looking at the resolution of a Cold War-era tension. The Americans had the best fuel-rich systems, the Space Shuttle, and the Soviets had the best oxygen-rich systems, the RD-180. For decades, it was assumed that you had to choose one or the other, because the complexity of combining them into a single full-flow cycle was too high. The integration overhead was thought to be terminal. And SpaceX's achievement is the successful merging of the branches. By solving the oxygen-rich nightmare through advanced metallurgy and computational fluid dynamics, they have moved past the era of compromised rocketry. They have built a machine that accepts the most dangerous chemical conditions possible in order to harvest the maximum possible thermodynamic reward. And this is why the Raptor 3 is the holy grail. It isn't just that it is powerful, it is that it survives an environment that, by the laws of basic chemistry, should be impossible to contain. It is a triumph of materials first engineering, where the software-like agility of SpaceX's design team allowed them to iterate through hundreds of alloy variations until they found the one that could stand in the heart of the oxygen hurricane without flinching. And the engine is no longer fighting the oxygen, it has tamed it. And by taming the oxygen-rich pre-burner, SpaceX has unlocked a level of energy density that makes the journey to Mars not just a theoretical possibility, but a mechanical certainty. This mastery of internal energy is what sets the stage for the next leap in the engine's evolution, the relentless pursuit of absolute efficiency. And with the chemical beast of oxygen-rich combustion finally caged within the walls of proprietary superalloys, the focus shifts from mere survival to total optimization. The true genius of the Raptor 3 lies in how it uses this hard-won stability to squeeze every possible joule of work from its propellant, a process we explore in 4.4 Efficiency Reimagined, maximizing every drop of energy.